Okay, so our prevalence now is 1% instead of 20%. Okay, not a lot of people have nickel sensitivity. It's probably closer to the real population prevalence. Okay, so if we have 1,000 people and a prevalence of 1%, how many people would be sensitive to nickel? 10. Yeah, yeah, 1% of 1,000 is 10. If we have a test that's 80% accurate in identifying those people, then how many people would test positive? 8. There you go. Okay, negative, false negatives would be 2. Okay, now our sensitivity to the test, now our specificity now is a little bit different. Okay, we're at 90% specificity. That means that the remaining 990 people, right? 90% of the time we'll correctly identify them as not being sensitive to nickel. Okay, and what would that be? What's that number? 881? Did I hear? 881 or 891? 891. Oh yeah, okay. Because it's going to be the other one's going to be I guess. Okay. So what does that leave us with? 90. Is 89, right? Am I right? 99. Okay, 99. So 10% of 990. That's the number of people that wound up that specificity to correctly identify. 1 minus 90% is 10%, which would be the number of people that were not correctly identified by the as negative by the test. Okay, so let's take a look at our positive results. How many people tested positive? 107. Okay. How many people tested negative? Yeah, 893. So what is now 107 people using this screening test that worked so well before? 190, 100, excuse me, 107 people tested positive with the same test. How many have actually have a nickel sensitivity? Only 8. So what's the positive predictive value of this test? 0.0, 0. What was it? I'm going to say 7%. Okay, am I right? Am I close there? 7%? Okay, I'm going to say roughly 7%, so we don't have to get into a fight over this. Okay, so now we went from a positive predictive value of 2/3, 67% that we had when it was 20% prevalence, same test. Now it's down to a 7% predictive value. 93% of the people that tested positive don't have a nickel sensitivity. Not such a great test. Is this unusual? I mean, is this something I made up that doesn't happen? No, in fact, there are a lot of tests like that. Anybody come up with any couple of tests that are like that, where it's a low prevalence disease, but you test a lot of it's low prevalence in the population, but you test a lot of people and you get a lot of false positives. What's that? I didn't hear that. Oh, yeah, I guess patch tests. Do you have that? Yeah, I guess because very low prevalence, right? And if you do that patch test, even if it's 99% specificity and sensitivity, you're going to get a lot of false positive because you have very few cases in a developed country. Okay, well, I guess you get more now, right? I'm teaching at Hunter, not at Hunter, I mean at Rutgers, and they made me they made me fill out 9,000 forms and take a TB test in order to test there. And I'm not sure, what that's all about, but I guess they got a lot of foreign students that come in from countries where there are relatively higher prevalences of tuberculosis. So I guess they just, rather than single out the students coming in from other countries, they just test everybody, do blanket testing for everybody, which is a little bit of a problem because then if I tested positive, if I were a false positive, then you'd have to go through more extensive testing, and I can't imagine it would be pleasant, right? I know what they would do. I guess an chest X-ray, yeah. Okay. So, and then if they saw something weird on the test, they've got a false positive on the chest X-ray. Then there's a biopsy, and then yeah, exactly. And trust me, when you're my age, if they do a CAT scan on you or a chest X-ray, they're going to find something without a doubt. They're going to find something interesting to hound you with. Trust me, when you get there, you'll know. So I mean, that's the problem with a lot of this. Same thing with PSAs for a protein-specific antigen for prostate cancer, right? They test the entire male population over 50 years old, and for relatively low prevalence cancer. So they wind up with a lot of false positives, and that winds up doing in all sorts of nasty diagnostic tests that follow that. Pap smears, same thing, right? Breast cancer screening, Pap smears, a lot of other tests have this property. So that's the deal. The real positive predictive value, the value of these tests very frequently is dependent very often on the more on the prevalence and how good a test it is really, prevalence in the population. There are cases where they use tests that don't have great use tests, diagnostic tests a lot more effectively by focusing on populations that they think might have the condition. For instance, there's anybody ever hear of a nuclear stress test? They inject you with a radioactive dye of some kind and radioactive material, and it has some affinity, for, I guess, for muscle tissue or something like that, heart muscle tissue, particularly. And then they screen you to see if I guess, if this is absorbed evenly by your heart. And areas of your heart that are not getting good blood flow don't get this material, don't accumulate this material as much as others. The prevalence, I think the specificity of it was in the 80% range, the sensitivity was in the 80% range. But you don't walk in and screen the whole population. You only get that test if you've had if you're symptomatic, or if you've had a suspicious normal stress test, and they want to go further with it, right? Certainly better than getting an angiogram, which is, has risks, a lot of risks associated with it. Right. So, but they use that test a little bit more rationally because they focus it on a population that they think has a higher prevalence of heart disease, or the kind of heart disease that they're looking for. Okay, so now let's take this to the next step here. Let me see if I can't get this out of my way. Okay, let me get my notebook back. Oh, what happened here? I must have closed it. Oh, that's an old one. Okay, won't worry about that. Okay, so now I'm going to take one of these cases that we just worked with, and we're going to apply Bayes' rule to it. Okay, so this is D plus, disease negative, test positive, test negative. Okay, I'm going to make it a little less specific. And I'm going to say we have our population of 1,000 people, and I'm going to say our prevalence. In this case, I'm going to say our prevalence is 10%. Okay, just for the hell of it. So we're going to have 100 people that actually have the disease, and I'm going to stick with our specificity, our sensitivity of 80%, and our specificity of 90%, same as we had before. So out of 100 people, 900 people don't have the disease because the prevalence is 10%. We're going to have 80 people that are correctly identified. These are true positives. Okay, we have 20 people that have the disease that test negative. These are going to be false negatives. Okay, sometimes it helps in the beginning if you haven't worked with this much to just kind of stick that up in the corner so you keep it straight. Okay, so out of the 900 people that don't have the disease, we identify 90% of them correctly, 810. And did I get that right? No, 90, right? And 810, right? Yeah, I did. I got it right. Oh yeah, the difference was before it was different prevalence. Okay, so now, okay, we see 170 people tested positive, 830 people tested negative. Okay, so now, let me see. Let me see. So make sure I get this right. I could never remember this. Write it down somewhere. I know I made a note here. There we go. Yep. Okay. Okay. So when I talk about the positive predictive value, right, I'm saying the probability that a person has the disease given that they've tested positive, right? That's equal to my positive predictive value. Okay, just the same. That's just as I would say it in words. The probability that a person actually has the disease, given that they've tested positive. Probability that now, since we're only talking about the people that tested positive, okay, get the only people that are involved here, given that they've tested positive, that's 170. The number of people out of those 170 that have the disease is 80, right? 80 out of the 1,000 test positive, but it's 80 out of 170 since I'm only looking at the ones that already tested positive. So my positive predictive value is going to be 80 over 170. Okay, so now if you guys remember Bayes' rule, okay, it's going to be, let's see, probability of A given that B has occurred times the probability of B, oops, is equal to the probability of B, given that A has occurred, times the probability of A. A little bit sloppy. Okay, so let's take a look at what we're looking at here. Well, first of all, I'm going to look at this. I'm going to say that A represents the probability of having the disease. Right? That's going to be my A. And B is going to be the probability of testing positive. Right? So I can actually change this into what I'm working with. First, before I do that, I'm going to move this probability of B over to the other side. I'm going to put it down there. Divide both sides by the same number. I can move it over to the other side. So I'm going to look at this now, and I'm saying to myself, probability of A given that B has occurred. In our case, it's the probability of having the disease given you've tested positive. That would make A the probability you have the disease, and B the probability that you tested positive. Okay, so I'm going to change that around. Probability you have the disease given that you've tested positive. And that's going to be equal to the probability of B given that A has occurred. Well, what is A? A is the probability you have the disease. B is the probability you tested positive. Okay. Well, what's the probability that you test positive given that you have the disease? You have the disease in this test. What's the probability you're test positive? What do we call that? We call that the sensitivity. So I could take this formula here and I can start actually describing what's over here. Okay, this part here is just a sensitivity. Okay, and probability of A. What's the probability of A? Probability of A is the probability you have the disease. What's that? Right, that's sensitivity times the prevalence. That's what's on top. Now on the bottom is the probability of B. What's the probability of B? That's the probability that you tested positive. There's two groups of people here that tested positive. One group is the people that really have the disease. The other group is the people that don't have the disease. There's a percentage of each that have tested positive here. So really, the probability of testing positive, probability of B, right? Remember we said B, now is the probability of testing positive. Probability of testing positive, that has two segments to it, right? And it's mutually exclusive, so I can add them together, right? So let me see, how am I going to do that? Let's see. First of all, let's look at one population. Let's look at people that have the disease, right? People that have the disease. What's the probability of them testing positive? People that have the disease, the probability of them testing positive, right? Well, that's again, what is that? That's the sensitivity again. isn't it? Right? Plus the probability of having the probability, let's see, probability, let's see, now what's the probability of testing positive if you don't have the disease, right? Probably that's going to get a little bit, that's going to get a little bit hairier here, isn't it? The probability if you don't have the disease that you test positive. Well, the specificity is the probability that you that you don't have the disease if you test negative, right? 90%. Right? If you don't have the disease, 90% is the specificity. So I'm more interested in the likelihood that people who don't have the disease test positive. So that's going to be 1 minus the specificity, right? That's going to be the likelihood that people, in other words, the probability that people who don't have the disease test negative is 90%. The probability that people don't have the disease, don't have the disease test positive is 10%. 1 minus the specificity. Is that confusing enough? Okay. I see. You get my drift here? I'm looking at what the probability, so that's going to be 1 minus the specificity, the probability that you would test positive if you don't have the disease. Well, now that's the probability of that happening, but what's the probability in this population of someone not having the disease? Well, the prevalence was the probability of having the disease. So what's the probability of not having the disease? It's 1 minus the prevalence, right? So if I want a number in here for the proportion of the population that tests positive when they don't have the disease, it's going to be 1 minus the prevalence. I can barely read that myself. Times 1 minus the specificity. Right? So what do we have? We have all of the things that we know about the test: sensitivity, prevalence, and specificity. We have those elements in here within this formula for the probability of having disease if you test positive. In other words, a positive predictive value. We can apply Bayes' theorem or Bayes' rule, and using this formula with these three elements that we know already: sensitivity, specificity, and prevalence, about the test in the population, to determine what the positive predictive value is. So now, do we want to do this, and do we want to roll the dice and actually do this and see if it works? Yes.
No, we have to multiply sensitivity by prevalence at the bottom also,
Uh,
or the plus sign.
yes, you're right. Sensitivity times the prevalence. Yes, right, because you want the proportion of the population that has a disease, sensitivity times the prevalence times the sensitivity, right? Because this is the number. This is the proportion of the population that has the disease that tests positive, and this is the proportion of the population that doesn't have the disease that tests positive. And when you add them together, you get everybody that tests positive. You're right. We left out the prevalence there. That should be prevalence there also. Okay, shall we give it a try? Maybe I should try and rewrite this. Use this kind of paper this time. Okay, so I'm going to put up here. Oops. What happened? Oh, I need that one. Probability that you have the disease, given that you test positive. Okay, it's going to be equal to the sensitivity. I'm going to abbreviate it, times the prevalence, over the prevalence times the sensitivity, plus 1 minus the prevalence times 1 minus the sensitivity. Okay, so sensitivity times the prevalence. What was the sensitivity? 0.8, right? The prevalence was 0.1, right? So the top of this is going to be 0.08. Right? I'm just going to get rid of that 0.08 over the prevalence, which was zero point 0.1, times the sensitivity, which was zero point 0.8, plus 1 minus the prevalence, which was 0. 0.9, times 1 minus the sensitivity, which was 0.9. Which one? Specificity, you're right. 1 minus, I did it right here. I wrote it wrong there. Okay, so 0.9 times 1 minus the prevalence, oops, which is that. Okay, let's see if this works out. Let's see if we get a reasonable number. So I get 0.08 over 0.1 times that is 0.08 plus 0.81, which looks familiar, right? Doesn't this kind of look familiar when we were playing around with this up there? It's going to be equal to 0.08 over 0.09.
Is the 1 minus
0.9.
specificity?
1 minus the specificity. Oh, you're right. 0.1. I'm so bad at this. I'm more of a right brain person than a left brain. Levi is a left brain person. He's very precise, and he'll work out every little detail very carefully. I'm more of a right brain person. I tend to look at this like, kind of like the sensitivity person and so on and so forth, but I don't have the patience for the actual numbers. 0.1 times, you're right, 1 minus 0.9 is 0.1. And did I get the prevalence? This was the 1 minus the prevalence is 0.9, and this, yeah, it turned that it was the opposite of each other. So this is 0.09, I think. Yes, 0.09, 0.08. So it's 0.08 over 0.17, which is equal to, anybody got a calculator?
0.47.
I'm sorry,
0.47.
0.47. Okay, now let's roll the dice here and actually go back here and look at this. What is it? It's 80 over 170 is the prevalence. And I don't even have to work that out because if I look here, I got my 80 over 170, got the same ratio down there. So it worked out. It's a Christmas miracle. Yes. So it's pretty interesting, right? That you can apply this formula to this idea of positive predictive value or conditional probability in this case. So now you don't even have to build a table. If I told you the sensitivity, the specificity, and the prevalence of the condition in the population, sensitivity and the specificity of the test, and the prevalence of the condition in the population, you could just use those three numbers and apply the conditional probability, use Bayes' formula, to actually just regurgitate back to me the positive predictive value. I would get it wrong, you'd get it right, hopefully. Right. So, but then eventually I would, figure it out, after I tried it a few more times. Right. So it's pretty interesting. Right. Okay. So any questions on that? Because, this is going to come up